Thanks. Dear Heavenly Father, we thank you for this morning. Again, Lord, I just thank you for these students. Just pray that you be with us today. Help us to glorify you again, Lord, in what we do. We thank you that our righteousness, if we have any, it's not our own, Lord, it's yours. And we thank you for the grace and mercy you give to us each and every day. I just pray that you would, again, be glorified what we do this semester, Lord. In your name I pray. Amen. All right, so don't worry, I have not looked at your tests. So whatever you have done, it remains hidden, safe, secret, stashed away in the stack of papers that I will grade sometime soon. But we are now to chapter 12, right? Series. Right. So we're now about to embark in the study of what does it really mean to add together infinitely many things in some sort of systematic fashion. But before we can start that properly, we have to first talk about something which is known as summation notation. So talk about that for a few minutes here, and then I'll define a series for you and work some examples, hopefully. So summation notation, aka sigma notation. This is a capital sigma. Well, here's how it works. Let me give you an example first. How about that? If I have the sum, say k equals 0 to 3 of k squared plus 2k plus 1, all right? What does that mean? What this means is you take whatever expression you have here, right? And you plug in k equals 0 to start with. So I get like 0 squared plus 2 times 0 plus 1. This is the k equals 0 term, right? Then I plug in 1. So that would give me 1 plus 2 plus 1. Then I plug in 2. That's 4 plus 4 plus 1, right? Then I plug in 3, which would give me 9 plus 2 times 3, which is 6, of course, plus 1. So this is a really nice notation to really compactly, concisely, I should say, denote some sum of things which has a nice systematic structure to it. Now, of course, we can add the numbers up. What do we get? I don't know. 30. Does anyone else agree? We know that truth is based on consensus, so, right? Sorry. 4 plus 5. 5 plus 9 is 14. 23, 29, 30. Yeah, I agree, 30. Yeah. Now, of course, we could have also looked at this as what? This is the sum. K equals 0 to 3 of what? This is k plus 1 squared, right? So you could have done a change of variables here. You could have said, okay, well, I'm going to let j, all right? I'm going to let j equals to k plus 1. If I do that, right, then if k is equal to 0, what's j equal to? So if I change notation here, this is really the sum, right? This is really the sum j equals 1. And if j is equal to, if k is so k equal to 0 gives me j equal to 1. K equals to 3 gives me j equals to what? 4, right? So I could also look at this as the sum j equals 1 to 4 of j squared. Here what I'm doing is I'm changing the dummy variable of summation from k to j. Why did I do that? Well, to illustrate the idea for you, really. I mean, this is a silly finite sum. You could just do it. There's nothing much gained here. I hope what's gained is perhaps to show you this idea that we can make a change of variables when it's helpful to us like this. But you got to be careful. You have to change the bounds, right? This is the lower bound. That's the upper bound of the finite sum, right? Anyway, this gives you what? 1 plus 4 plus 9 plus 16, which is 30. I hope. Yeah, okay. Yeah. All right, so how do we define the sigma? How do you define, let me give you a careful definition here. So if you have the sum, we define the sum, say I equals 1 to, well, I'm going to be a little bit more slippery here. I'm going to say the sum I equals n sub naught to say, oh fine, I'll use 1, I'm sorry. It's better just to do this. I equals 1 to n of a sub I is equal to, now this is kind of sneaky, check this out, a sub n plus the sum I equals 1 to n minus 1, right, of a sub I. What kind of definition is this? By the way, is the audio working? Just to check it. Cool. It's a what? I need to do something else too, right? What's A1? What's the sum? What's the sum I equals 1 to 1 of a sub I? What's that equal to? That should be equal to a sub 1, right? So this definition I'm giving you right here, and here I'm assuming, of course, that the a sub i's are real numbers, all right? I suppose they could be complex or something else. As long as you could add the things, it would still make sense. This is a what kind of definition? This is a recursive definition, right? We've talked about these things before, right? Like, how would, just to work it out for a second here, what's the sum I equals 1 to 2 equal to? Well, my definition says it's a2 plus the sum I equals 1 to 1 of a sub I, which is what? a2 plus a1. All right. So anyway, this is sometimes useful if you have to prove something picky about a finite sum. You probably won't have to. We think it's more fair to only make you prove picky things about infinite sums, because this is calculus too. Sorry, little curriculum criticism there. But we are where we are, so we have to do what we're doing. So you keep going, and if you have the sum I equals 1 to n of a sub I, what do you get? You get a1 plus a2 plus dot 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 plus a sub n. And so like your textbook may well just define it to be this. And that's not too much of an abuse. That is what it is after all. All right? And as long as n is finite, there's really no ambiguity there. But just so you know, what I have above is a nice, careful definition. Any questions about this so far? What are the properties of finite sums? There's two big ones that are really nice. Number one, if I have a constant times a finite sum, you know what I can do? I'll write it out in the expanded notation. This is c times a1 a2 plus plus an, right? So what happens when you take a constant and multiply it times a sum like that? It just does what? Distributes through, right? That's ca1 plus ca2 can, right? But we can rewrite that in summation notation simply as the sum I equals 1 to n of c times ai. So we can pull constants inside finite sums like this. It's nothing more than the n-fold distributive property of real number multiplication and addition written in a nice, slick notation. Well, I think it's nice. You can disagree. It's a judgment call, but I judge it to be nice. Again, you may judge otherwise. All right, so another thing, if we take the sum I equals 1 to n of a sub I plus the sum j, oh, I'm sorry. Well, I could use a different letter even. I don't usually put a different letter here, but I will just for the sake of making a point, b sub j. Well, let me just write out what those are. That would be a1 plus a2 plus plus an, parentheses, plus what? b1 plus b2 plus plus bn again, just by the definition of the finite sum. What can you do then? You can rearrange these things, right? You could rewrite this as what, like a1 plus b1 plus a2 plus b2, right? Using associativity of real number addition. And then, hey, by the definition of the finite sum, we can write the end result as what? Now, what do you think? Should I use I or J on the final thing here? How many people vote for I? How many people vote for J? Okay, good news. You're all right. It doesn't matter. I could use K. The point is, this notation all means the same thing because this K, this I, this J, these are all so-called dummy variables of summation. If you think about it, it gives you the same expression, right? So it's kind of a stupid change of variables. Like I did an interesting one over here. I said J is equal to K plus 1, right? There we had to change the upper bound and the lower bound because the K and the J were genuinely different in their structure and function here. Whereas over here, you could just as well have used I and I both places here. It wouldn't have made any difference. Your question?
Can you only do that if they start at the same number and end at the same number?
Right. If the sums have different starting points or ending points, then you'd have to do something different. Like, for example, that's a great question. Here's a modification of 2. If you had something like the sum, let's say I equals 1 to n of a sub I plus the sum j equals 3 to n of b sub, let me use I. We can use I in both, right? B sub I. Then what you do, what I would do anyway, is I would say, well, that's a1 plus a2 plus the sum I equals 3 to n of a sub I plus the sum I equals 1 to n of b sub I. And this is an important idea. If we have discordant, if there's finite sums are not in concert, if there's some discord between their lower bounds or their upper bounds, then you can either throw out, right? Or sometimes you could even add, but usually it's easier just to kind of say, okay, well, that's the oddball. That's got the extra piece. I'm just going to write that separately, and then you can make the finite sum smaller like that.
Does that I have to be just be a 3? Mean I equals 3 for...
Oh, absolutely. Thank you. And so, you know, just to get to the end point here, this is a1 plus a2 plus the sum I equals 3 to n of a sub I plus b sub I, right? All right. Now the other sort of thing you might be asked, right, is to find a formula for something that's already written as some sort of patterned sum. Like, so let's look at one of those. I'll do 2 examples. So our goal here is to find a sub I and n and n naught such that the sum I equals n naught to big N of a sub I is equal to the following. See below, okay? Or over there. That's a different sort of below, but you'll follow. Okay, so how about this? 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. These are all what? Odd numbers. So you could write them in the form, so these are all basically of the form 2 times some number I minus 1, right? So, and that's for what? For I equals to what? Let's see here. Looks like 1. This is 2, 3, 4, 5, 6, 7. All right, so I can write this as the sum I equals 1 to 7 of 2i minus 1. How else could you write that? Some of you might be like, no, that's incorrect. You should look at this as, that's really like 2 times j plus 1 for j equals to what? That's 0. J equals 1, 2, 3, 4, 5, 6. Right? 2 times 6 is 12. 12 plus 1 is 13. You could also write this as the sum j equals 0 to 6 of 2j plus 1. Okay. Oh yeah, there is an infinite number of different ways we could express this, yeah. I suppose you could do something even even weirder. You could think of it in terms of grouping this and this and this and well, maybe not. I know there are other weirder things you could do, yeah. But let me not try to make it weird. I'll just leave it at that. So that's sigma notation, guys. So for a finite sum, it's really just a nice notation for just writing a bunch of things added together. There's really not anything terribly ambiguous about all this, right? I mean, okay, the formula can look different, right? But the analysis is relatively harmless. And there's really no reason not to teach this to college algebra students, for example. Okay? I mean, you'll find this in college algebra books. It may or may not have been taught to you, but, you know, that's kind of beside the point. Actually, we used to teach sequences in college algebra, I guess. Not me. It's kind of before my time, but. All right, so that brings us to what is a series. Now, when people talk about series, they're not really, what is a series? You could think of a series as being an infinite sum, I suppose. Let me give you the careful definition here. This is something you need to memorize. Here it is. Definition. If, as n goes to infinity, all right, the sequence of partial sums S sub n, I usually use a capital S sub n. He uses a little s sub n. But that's defined to be the finite sum, all right? K equals 0 to n, a sub k. So you notice that the sequence here starts at 0. All right? So we oftentimes look at sequences which start at 0. I hope that's not a big deal. I kind of told you sequences start at 1 before, and now we're throwing that out. I mean, our sequences start at 0, but that's not a big adjustment, right? Everything stays pretty much the same in terms of the sequences. All right, sequence of partial sums, S sub n equals sum k equals 0 to n, a sub k, if tends to a finite limit L, then this if is followed by that then. We write the sum k equals 0 to infinity of a sub k is equal to L. Furthermore, we say, in this case, of course, the series sum k equals 0 to infinity of a sub k converges to L. All right. We call L the sum of the series. All right. If the sequence of partial sums diverges, we say that the series diverges. So everything I've written in black concerns the case that it converges, all right? If Sn does not converge to L in the reals, all right, then we say the series sum k equals 0 to infinity of a sub k diverges. All right. Let's look at some examples. What if we add 0 to itself infinitely many times? Very silly example. How about the sum I equals 0 to infinity? Oh, I'm sorry, he's using k. I'll try to use k. Okay, k equals 0 to infinity is 0. So what's a sub k in this case? It's 0, right? So can you calculate what's the nth partial sum? S sub n is equal to the sum. See here, k equals 0 to n, right, of a sub k, and what's that equal to? Zero plus 0 plus 0 plus, yeah. Kind of, yeah. Which is just 0 again, right? So this one's pretty easy to calculate. What does Sn do? Sn goes to 0 as n goes to infinity, right? So, therefore, the sum k equals 0 to infinity. In other words, this series of adding 0 infinitely many times does indeed converge to 0. The sum of this series is 0. That's good. We should like this, right? It would be disturbing if anything else happened. What happens if we add the number 1 together infinitely many times? What's the nth partial sum if we're just adding 1 repeatedly? So here a sub k is equal to 1. Then what's s sub n? It's equal to the sum, right? K equals 0 to n of 1, which is what? 1 plus 1 plus 1 plus da 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 plus 1. How many ones? How many copies of 1 are there if we're summing from k equals 0 to n? What's that? N is almost right. It's n plus 1 of them, right? So in fact, this is n plus 1, right? What happens to that as n goes to infinity? This goes to infinity, right? As n goes to infinity. Therefore, the sequence of partial sums diverges. Thus, the sum k equals 1 to infinity of 1 diverges. Not especially surprising, but there it is. Yep.
For when it's S sub n, why is k equals 0 and then the other times k is equal to 1?
Oh, this was supposed to be 0. Thank you. That's a typo. But you could, in fact, of course, look at series that start at 1. Or you could even look at series that start at like -7. The point is they have to have a start, and they go on. Yeah.
Why is S sub n equals 1?
Because it starts at 0. Like, look at 1. K equals 0 to 1. 1 plus 1, 2. All right. My third example will be the sum. Let's say k equals 0 to infinity of r to the k, where the absolute value of r is less than 1. Phew, I was worried it was later. We're actually at plenty of time. Cool. Now, so let me just take a second here and write this out in the other notation, you know. In other words, this is 1 plus r squared plus r cubed plus dot 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 equals what? So what do we have to do? The only thing we can do at the moment is try to calculate the nth partial sum, right? And then take the limit as n goes to infinity to see if the series converges or diverges. All right? So calculating the nth partial sum in the first two examples was kind of like a yawn. This one is a little bit harder, but it's a homework problem you've done before, right? So what is it? If you look at Sn, what is Sn? Right, again, the sum k equals 0 to n of r to the k, which is what? That's 1 plus r squared plus r to the n. So if I look at r times Sn, what does that give me? Let me add a little bit more detail here. R and n minus 1 plus r to the n up here. So I end up with r to the n plus r to the n plus 1. So what I did was I took the nth partial sum and I multiplied it by r, right? Just like the textbook led you to do in one of the homeworks I assigned before, right? And then what do? Calculate the difference. If we take, you know, Sn minus r times Sn, what does it give us? Lots of cancellation, right? So we end up with Sn minus r times Sn equals to what? Let me illustrate the cancellations in the step above. So as I subtract this, right? Basically, I'm doing this right now, right? So to speak. So these r's cancel, right? These guys cancel. All the way on out until we get to this one cancels. This one cancels one I haven't written. That one cancels one I haven't written. All you're left with is this one and that one, right? So we get 1 minus r to the n plus 1. So then you do a little bit of algebra here. This is Sn times 1 minus r, right, is equal to 1 minus r to the n plus 1. Solve for Sn. What do we get? Sn is equal to 1 minus r to the n plus 1 divided by 1 minus r. Do you guys follow? It's important that you follow this example. This is maybe the most important example I'll do the next few weeks. We'll use this over and over and over again past this point. I mean, this is the linchpin of like dozens of deep and interesting mathematical theorems. In some sense or another, come back to this. You'd be surprised. Now, what happens as n goes to infinity, given the condition that I wrote up here? If you have a real number, magnitude less than 1, and you take it to the n plus 1 power and take n to infinity, what happens to it? Right, this goes to 0. So this whole thing goes to 1 over 1 minus r. So we observe that the nth partial sum converges to the real number 1 over 1 minus r. Thus, the sum of this series, k equals 0 to infinity, of r to the k, is equal to 1 over 1 minus r. this is the precious and famous geometric series result. Although at the moment I'm just talking about the convergent case. It's a convergent geometric series. I'll put that in parentheses because I don't insist you call it a convergent geometric series, but it is a convergent geometric series. What would be an example of a divergent geometric series? Well, I suppose I already did one of them here. Kind of a stupid case. Here's r equals to 1. 1 plus 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 1. In other words, 1 plus 1 squared plus 1 cubed plus 1 to the 4th plus 1 to the 5th plus 1 to the 6th plus 1 to the 7th plus 1 to the 8th and so forth and so on, right? That diverged. And the same is true if you take the absolute value of r being greater than 1 or equal to it, it diverges. By essentially the same calculation, right? Nothing would change if I replaced this absolute value of r less than 1 condition with, say, absolute value of r greater than or equal to 1. Let me use a different color here. So like let me say, if the absolute value of r is greater than or equal to 1, then the sum, I'll just write it as a separate example just so you have a kind of split off so we're not confused. Sum k equals 0 to infinity of r to the k diverges. I would say that's a divergent geometric series. And the reason it diverges is since S sub n, right, is equal to, and let me see here. So note, r equals to 1 is example what? 2. And if r is greater than 1, then by the same calculation as in example 3, we find the nth partial sum is what? It's 1 minus r to the n plus 1 over 1 minus r. And this does not converge to L in the reals. So this is, Sn is a divergent sequence. Since r to the n plus 1, does not converge to any L in the reals, as the absolute value of r is what? Greater than 1. I'm sorry, I should say absolute value of r here. I would say it diverges to infinity, except I want to allow the case that r is like minus 2 or something like that. And if r is a negative number with magnitude larger than 1, what happens is the sequence of partial sums, it's going like way up, and then way down, and then way up, and then way down. And it just oscillates between plus and minus infinity as it goes on. So it doesn't really diverge to infinity, it just diverges. All right. Any questions? Let me apply this to something. How about this? How about a decimal? About a decimal number? You realize you've been using series all along? Whether anybody told you you were or not, you were. For example, 0.99999999999. Okay, you get the idea. Repeat it, all right? What is that? Let's write it. That is really, by definition, I would say 0.9 plus 0.99999999999999999999999999999 0.009, right? Plus 0.009 plus 0.0009 plus dot, 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 dot. That's a series. Oh, I'm sorry. If you don't mind, well, stink. I guess I need a little theorem before I can do this example. If you'll forgive me, if we'll prove this theorem shortly. If C is a real number and the sum k equals 0 to infinity of like a sub k is equal to L, then the sum k equals 0 to infinity of C times a sub k, guess what it's equal to? CL. Okay. In other words, for convergent series, for series which have a sum which is in fact a real number, you can pull constants inside or outside. Now that's relevant here because you see what I need? I need kind of like a slight beefing up of examples 3 and 4. What I need is the following result. And this is usually what's referred to as the geometric series. The sum k equals 0 to infinity of a times r to the k is equal to a over 1 minus r, provided what? We need the absolute value of r is less than 1, right? So this is the sort of full. And so, I can look at this as, say, a plus ar squared plus ar cubed plus dot, 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 dot. A is the first term, right? And so here, a equals what? A equals 0.9, right? What's r equal to? .1? Let's see here. Yeah, I think that's right. So I multiply by 0.1 to get from here to here, to get from here to here, to get from here to here. It has to, if it's geometric, it has to be able that the case that if you want to go from one partial sum to the next, you have to be able to, multiply the last thing you added by r and get to the next one. Sorry, I'm being a little bit imprecise in my language there, but I'll try to be more precise when we get to something a little bit more. In order to see something, not being geometric, I mean, the choice of whether or not a series is potentially a geometric series is an interesting question, okay? And it's not a hard one to answer, but it's a hard one for you to even appreciate right now. We don't have enough examples, so I'll shut up about it. So what is this? What is this? So how about that? R equals to 0.1 certainly fits the bill, right? This is a convergent geometric series. What does it converge to? 0.9 divided by what? 1 minus what? 0.1. What's this equal to? 1, yeah. There you have it. 0.99 repeating is in fact equal to 1. There's the proof. That's what's implicit within the proof, is understanding that decimal real numbers, and when we accept things like unending decimal representations of real numbers, what you've accepted once you accept that is that there's something called an infinite series, and it can be used to represent numbers. This is a relatively new idea. It only predates Newton by about 50 years or so. Without this idea of representing numbers by unending, basically unending series, and that really is the decimal representation. You would, I mean, how would you represent very, very, very small numbers if you only could work with fractions? Right? How do you compare, like, 13 over 1,000 versus 7 over 207? You actually have to think about it, right? If you compare decimal numbers, which one's smaller than the other? You just look at them, right? So much of calculus is based on approximation, right? Like, what is close to something else? And so, I've read it in books before, like, that makes it right? But no, I mean, some people would say that part of the reason Newton was able to do what he did was precisely because decimal numbers were available for him to work with. It's a big deal, the existence of decimal representations of numbers. So let's see here. Is there, this definition, what are we saying? What is the sequence of partial sums? I never actually wrote it out for you guys yet, have I? What is that sequence? If you write it in terms of like a list, what would it look like? So I would say this is the range of the sequence, but it looks like what? It's in this A0, right? What's the second thing in the sequence? A0 plus A1, right? What's the third term in the sequence? Right? And then the nth term in this sequence, well, it's actually the n plus 1th term, I suppose, right? Because we start at 0, I mean, that messes up the counting, right? So by definition, like if you want me to condense this definition down to a slogan, it's simply this, right? A series converges to its sum, right? If and only if the limit of the sequence of partial sums exists. In other words, the convergence of a series is completely governed by the convergence of its sequence of partial sums. If the sequence of partial sums diverges, the series diverges. If the sequence of partial sums converges, the series converges. All right? I do expect you to memorize that soon. Like, I'll probably quiz on this tomorrow. All right? Because if you don't understand that definition, you won't be able to follow anything else we do. And students have trouble understanding this definition. You guys are like, nodding, some of you. But devil's in the detail. Now, what I've shown you today is precious and weird. For example, this one. So that would be like 1 plus a 4th plus a 9th. That is not geometric, right? If you look at the next term that you're adding, it's not a simple multiple of the one before, right? Not geometric, for an example. If you try to calculate the nth partial sum of this, you will not be able to do it. Most things that you write series of, you can't actually calculate the nth partial sum. So what we need to do is to find other ways of determining whether it converges or diverges. And that's where this laundry list of convergence, divergence tests we're about to come to will come into play. It happens to be that this is equal to pi squared over 6. What's pi squared over 6? Can you somebody punch in their calculator for me just real quick? Like 9 over 6, what is it? $1.5-ish. So here's 1.25. What's that? $1.583. What do you say? Oh, you added a third, added a ninth. Anyway, you guys get the idea. But why that? I guess you could ask Euler. He discovered it about, I don't know, 300, how many years ago? I don't know, a few years, maybe 400 years ago now? I forget. I think it's been a few hundred years we've known this. Anyway, I shut up.